for sticking around. Kunal is our last speaker for the day. You might have to do a bit of motivational speaking to keep everyone awake. I didn't have my afternoon coffee, so I'm starting to feel it. So Kunal has been a PhD student with us since fall 2016. One of the most senior PhD students at LSU. This year, he's been on an extended visit to Los Alamos, visiting the group of Patrick Cole's working on variational quantum algorithms. He's going to tell us about some work that he did there. Take it away.
Thanks, Mark, and thanks for organizing this and also for nominating me for giving a talk. So as Mark said, I've been working at Los Alamos Lab with a group, and we did a couple of projects, and I'm going to talk about one of those, which you can find on arXiv. I did this work with many co-authors. So Zoe and Marco, they are postdocs at lab, and then Lukash, Patrick, and Andrew, they are staff scientists. And yeah, Zoe actually was a summer student just like me last year, and then she moved from, she hasn't moved from UK yet, but she joined as a postdoc now. This is the outline of my talk, and as Mark said, I'll try to make it interesting since it's the last talk. In my whole talk, I'll never call it no free lunch. I'll always refer to as NFL. And I'll define the notion of classical NFL theorem, which is there in the classical machine learning, which has been there for a long time. And then I'll try to develop the notion of quantum NFL theorem. I'll describe the main results along with numerical implementations as well. And then I'll end my talk with some open questions we have. So before defining the framework of no free lunch theorems, let me just go to a very simple example. You all use, let's say, Google Photos, or let's say you just search photos on Google. You know, if you search for cat photos, all the cat photos appear. So that can happen just because of supervised machine learning. So the algorithm works as follows. Let's say if you have a big data set of, let's say, cat pictures, you can divide that data set in terms of test and training data. So in this picture right now, I'm just showing you training data. And as humans, we are good at image detection, right? If you see a cat or dog picture, you can definitely say, oh, it's tag or it's dog. So we are good at labeling, but how do you teach it to some algorithm? So when you say, how do you teach it? You have to ask, what do we mean by teaching? We want to figure out a function from a picture to corresponding labels. So that means we are trying to figure out some function which is taking you from training data to output labels. And when you say algorithm, what do you mean by algorithm? Well, you can imagine, let's say there is neural network, which I hope everyone knows. And even within a neural network, you have different parameters. You have to optimize them so that collectively we can call as an algorithm. Now, what is the goal of this whole procedure? The algorithm sees the picture, and by picture, I mean the pixel data values. And then it tried to spit out the labels. And on the training data, we just tell the algorithm, hey, no, you label it in the wrong way. And through the optimization procedure, algorithm is trying to change the parameters involved in the hypothesis such that the error goes to zero, or it becomes, as minimum as possible. So I'm just defining these terms because I'll be using these terms in my talk. So hypothesis is something algorithm is trying to come up with, and trying to come up with in a way that it matches with the function on the training data. And suppose you have trained it well on your training data. Next question is, how well does it perform on the test data? So let's say I click a new picture of a cat and I ask this algorithm to figure out whether it's a cat or dog. Can it predict it very well? So in this whole framework, there are mainly three big questions. One is trainability, expressibility is the second question, and then scalability. So trainability, there could be trainability issues, right? Because whatever function you are trying to go after, it could happen that the cost landscape is very weird. By that I mean that maybe there are many local minimas, and then maybe there are many flat regions. So you might not be able to train properly. And I'm just giving this example of cat and dog, but this can be generalized to many examples in physics problems as well. And right now I'm just talking about classical machine learning. Expressibility is, suppose the function required it to be, let's say, some nonlinear function, but let's say you're trying to just hypothesize is through using, let's say, linear function. You can never do it, right? You will be approximately doing it, but maybe it's not good enough. So you have to come up with answers such that you can express it well. And the final question is scalability, which is, suppose your data set is very, very big data set, and if you are just training over a small subset of the big data set, can you really generalize your predictions? Can you really predict well on the test data? So this is just an outline of the whole framework, and we can now formalize it in terms of math equations. So let me just do it. So suppose you have discrete sets, x and y, and they are finite. So the dimensions are dx and dy. And your goal is to mimic this target function. So target function is some function, and it's a deterministic function for now, which takes you from the set x to y. And as I said, whatever algorithm you come up with, you have to define some training set for this supervised learning scenario. So what do we mean by training set? You have to have some sort of training pairs, xj and yj, where xj is in x and yj is f of xj. And you can define the dimension of the training set, which is going from, let's say, 1 to t. And the next task is to come up with hypothesis. And our goal is, given a training set, our goal should be to just make the error go to 0, at least on the training set. So that also you can define mathematically, which is, if you apply hypothesis on xj, where xj was in S, then it should match with the action of target function on xj. So once we have defined these assumptions, the next question is, how can we quantify the performance of HS? So we have to define some sort of error model or error notion for quantifying whether we are predicting well or not. So we can define as follows. So suppose I have x in the curly x, which was my input data set, and I sample x with some probability pi x. What I'll do, I'll try to find the probability of error in predicting the outcome. So here you can see that what I'm trying to say is that probability of fx not being equals to hs of x. All right, so what is NFL theorem? So NFL theorem tries to quantify the following expression. So if you look at this expression, here I have the risk function, and what I'm doing now is trying to take the average over all training set and all possible functions. I should clarify that when I'm saying all training set, then I have fixed the dimension or the size of the training set. So I'm saying that S is a set of dimension t or size t. And when I'm taking the average over S, that means all possible training sets with size t. And when I say function, that means all possible deterministic functions taking me from curly x to curly y. And why this quantity is useful? Because this quantity is going to tell us, irrespective of your optimization procedure, what is the average error. And as it turns out, I've already mentioned the result, which I will explain in the next slide. Lower bound on this average error depends on the size of the training set and also the overall dimension. And this is an existing result in the classical machine learning theory, where you can see now that if the size of the training set was equals to d, this lower bound will become 0. And that makes sense because if your training set was the whole set, then there is nothing left in the test set. So then the lower bound should be 0, and which is also achievable. But suppose if you say, oh no, I'll not use the whole set, rather I'll just use some small subset, then the lower bound can quantify this average error. You can also phrase it in another way, which is the following. Suppose I have two different optimization methods. This bound is telling us that on average, both optimization methods will perform the same. Or there are instances where first optimization method might fail and the second can do better, and vice versa. So that's why this notion of average error over all training set with some size t, and then average error over all possible functions is important. So I can just walk you through the proof of it, which is quite simple, but I'll not make it boring, so I'll just spend like 1 minute on it. So we can just open the equation, right? The expression for RF, which I defined here, I just opened it and I have these two averages going on. And let's suppose that we could actually train everything on the training set. We can train perfectly. And now the question is, what is the error on the test data? So that's why the first expression is gone, the first expression in this line. And then in the next line, I just pick the second term, where X is not in the training set. And now you can argue that if you average over all possible deterministic functions, then the probability error will be given as d minus 1 over d. And I can discuss this after my talk if someone has any question how to get that. But this is it. This is the proof of classical NFL theorem. And that's why I really like it, because it's very simple. But when we go to quantum, we'll have to deal with more assumptions and subtleties. So from here, I'll move on. And I just want to make one more statement, which is the classical NFL theorem is an information theoretic bound. Why? Because suppose if I tell you that the function was 1-to-1 from the input set to output set, if the function was 1-to-1, and if you have trained on, let's say, some subset of the whole set, then you have some information now for the rest of the data, right? For the test data. So using that information, you can improve the bound. So which is this different bound, which is, let's say, you can also find the NFL for permutation matrix, which is I'm saying in terms of functions, which is 1-to-1 functions and onto as well. And they're using the same derivation, but just making more assumption about the function, you can get this bound where now you can see, let's say my input data and output data were dimension 3 and my training data was of dimension 2. If I have trained perfectly on the two-dimensional system, then I definitely know the answer on the test data, which has just one element. Why? Because it is 1-to-1 and onto function. If I know already outcome for 2, I know for the third one as well. So from here, I'll now talk about quantum NFL theorem. So I just try to make the one-to-one analogy from classical to quantum. So I think we all know that in the quantum case, now we have to talk about Hilbert spaces. So you have your input Hilbert space Hx and output Hilbert space Hy. And for now, let's assume that the dimensions are same. And in quantum mechanics, the analogous to function is the unitary, which is, let's say, taking you from Hx to Hy. And similar to classical case, now we have to define training set and hypothesis. But now we can do something more than what we could do in classical case, because quantum mechanics allows us to have entangled state. So what we are trying to say now that the training data also has a reference system R, where unitary only acts on system X, not R. So there is identity acting on R. So training set consists of these pairs, psi j and phi j, where psi j is in Hilbert space consisting of X and R. And then phi j is defined as when you apply U on psi j. And U is only acting on the X part, not the R part. And then using this training data, we have to come up with a hypothesis which tries to mimic this unitary U. But then we all know that we can, let's say if I give you a quantum state and if I say, hey, there is some unitary applied on this state, can you figure out what is the outcome? We can only figure it out up to a global phase. So that's why the hypothesis assumption is the following, that if you apply this hypothesis on psi j, it should match with the outcome of U psi j up to some global phase. And this is something we use in the proof to get the quantum NFL bound. So now the next question is similar to classical case. How do we quantify the error now? How do we quantify whether we can generalize the hypothesis to even test data? So the risk function is defined as follows, which is 1 minus this term where we have this Hilbert-Schmidt distance between U and V. Why did we choose this? Well, this function is easy to deal with, or another motivation is that this is equivalent to 1 minus average fidelity. between U and V. So you, let's say, apply U on some state, some pure state, and apply V on some pure state, take the overlap, and then average over all pure states. So this is equivalent to 1 minus average fidelity. So the next thing is, what is the goal of quantum NFL now? The goal is same as the classical case, where now we have to average over all possible training set. And again, when I talk about training set, let me just go back. Here again, I have to talk about dimension, this T. So when I'm saying dimension is the number of training pairs I have in my training set. So I have to average over all such training set and all possible functions, which means all possible unitaries. And I'll show on the next 2 slides, by using simple arguments, you can actually derive this bound, which depends on a couple of things. Maybe I missed talking about this R. Let me just go back here. So if you look at the training set, I just said that, okay, I have some entangled state between system X and R. Now, when we talk about entangled state, which is bipartite entangled state between X and R system, we can talk about the rank of the state, Schmidt rank of the state, which quantifies how much entanglement you have with the reference system. So that's what R is. R is a Schmidt rank of this pure state. And when I define this set, I also fix the rank. So this set consists of entangled states with fixed rank. And that's why the bound depends on the rank. So given rank R, the average over all possible training set with size T and all possible unitaries is lower bounded by this function. And I'll spend more time on this function after 2 slides. So let me just give you a brief sketch of the proof. And this, you can ignore this side because I've already defined these things in previous slides, but I just kept it so that you can just recall. First is this function, what is training set and what is hypothesis. So we just define a couple of things, which is W, which is in terms of Q dagger V. Psi j, I just write in terms of Schmidt decomposition. And then using this hypothesis assumption, which I have at the bottom on the left side, I can get this equation, which is that exponential of I theta j is equals to something. And using the assumption that, okay, modulus of any exponential I theta j is 1, and sum of Cjk is equals to 1, which follows from the Schmidt decomposition, I get finally this condition that all these beta jk is equals to E of I theta j. So all I'm doing now is writing this W, this overlap, because that appears in my risk function. So I'm just trying to write W now in the basis of my training set vectors. If I do that, I can write my W in the following way. And here I use the properties of unitary matrix that if the modulus of each row and each column has to be 1, and then 2 different rows should be orthogonal, and so on. Now, all we need to do is, let's say I have to do the averaging over this term. Now I can translate this averaging to averaging over this Y. So this Y corresponds to the submatrix of my big W, which I have not trained on. So I only trained on this part, and where I have these nice complex numbers, and rest of the terms are 0. But this Y is completely random to me. And that's why we do this hard averaging over Y of this function, which I will not go in detail because I don't have time. But eventually, using hard averaging over unitaries, you can reduce it to R squared T squared plus 1. And that gives you the quantum NFL bound. What is the nice thing about quantum NFL bound in comparison to classical NFL? If I consider, let's say, R equals to dimension of the system, which means I have maximally, I should not say maximally entangled state, but I have, let's say, n qubits in my system X. And if I take n qubits in my reference system as well, then you just need one training pair to make this lower bound 0. So on the other hand, if you look at the classical case, as I was explaining earlier, that if you don't have any information about the function, it's just some deterministic function, then you need E equals to D to make this lower bound go to 0. But in the quantum case, depending on the rank R, so suppose, let me just describe one more special case when R is equals to 1. That means there is no reference system. If there was no reference system, then the quantum bound actually becomes similar to classical bound in the sense that you need exponential number of training pairs to uh, to make your average error go to 0 or the lower bound go to 0. But as soon as you bring the reference system in this whole setup, then depending on the rank R, you don't need to have a large number of training pairs in your training set. So I think I now will explain, since I have 10 minutes, I'll just go to the, before going to the numerical implementation, let me just also explain, even though I was just trying to compare it with the deterministic function, unitary in the quantum case can describe probabilistic processes, right? Because quantum mechanics is a probabilistic process. So in the classical case, what are the analogs of, let's say, unitaries? We can say that, yeah, we have stochastic maps, right? We have stochastic processes. So even for these cases, we get the bound. We get an analytical bound for stochastic maps. And for bistochastic maps, we reduce the expression of this average error to an extent, and then after that we calculate it numerically. So this is the bound we get for stochastic maps, which looks quite complicated, but this is what it is. And if there is interest, I can explain how we get it later on after my talk. All right, so once we have all these bounds, so classically we have, let's say, for any deterministic function for permutation matrix, which corresponds to surge 1-to-1 and onto functions, and then probabilistic functions as well. I should not say functions, but maps, stochastic and bistochastic, and then quantum NFL. And in that quantum NFL, we have all possible range, right? Because we can have where R is equals to 1, there's no entanglement, and R is equals to D, where we have like maximal possible entanglement. So we verify these bounds on both quantum computer and quantum simulator. So this is like very simple simulation, because all the bounds which I introduced to you just now, they were calculated without any noise. But then if you want to do it on quantum computer, that means there will be noise. So we just did very simple exercise where it was just 1 qubit unitary, and the goal was to learn that unitary. So for that, we use this cost function, and this is just designed using the training data, right? Because as I said, psi j was input training data and phi j was output training data. And here, you just do the averaging over all possible training pairs you have. So we do it for 2 cases, when you have just 1 training data and you have 2 training data. And this was done on Rigetti I think it was 4 qubit system, but we didn't need it because we just had to use maximum 2 qubits. So we want to learn a single qubit unitary, and even if you introduce a reference system, you can just have one reference system, 1 qubit reference system. So here you can see that the blue line corresponds to when you don't have any entanglement. So we have these 2 points corresponding to 1 training pair, and then this corresponds to 2 training pair. And the red curve corresponds to the case when we have entanglement with the reference system. So again, you can consider the case when you have 1 training pair of entangled state, or you have 2 training pair of entangled state. And as I said, the classical cases we just plotted just to see where they lie for a given value of t. So the entangled case beats the classical bounds, where we have plotted 2 bounds. From the classical case, we have 4, right? Because of, as I explained. So we here plot the deterministic one and the stochastic one. And even though this was very simple, this was just done for proof of principle, that even with the noisy quantum computer, we could show this feature that you can learn unitary with the entangled data set. Then we also performed numerical simulation with quantum simulator, and we could go for a higher number of qubits. And in this case, we varied the rank from 1 to, let's say, 64. So we did it for 6 qubits. So that means you can have rank up to, Schmidt rank up to 64. And here we are plotting all possible plots. So we plot all classical bounds for deterministic and permutation, stochastic and bistochastic. And the x-axis is again the number of training pairs, and the y-axis is average risk. And again, from this plot, you can see that as soon as your rank is 64, which means you have this full entangled state, then the average risk is 0 irrespective of what number of training pair you have. And that's the message I was trying to convey, that this is why it's different from the classical case, where for the classical case, you have to have T equals to either D or D minus 1. So D minus 1 when you have, let's say, permutation matrix. And but in the quantum case, if your rank is not 1, if it is beyond 1, then you can continuously decrease the size of training set and easily generalize it to test data. And with that, I'll just explain the open questions. So in this whole scenario, I was saying that, okay, we have this training data consisting of entangled pairs. But now you can ask this question, like how will we get these training pairs? So either we can design a game where someone is giving me a problem and then they're just giving me the circuit representation or circuit description of those training pairs, both input and output, and then I try to learn the unitary. Or Los Alamos lab group, when Sumit visited, they came up with this algorithm, quantum assisted quantum compiling, where the goal was that, let's say, from some classical method, you figured out how to implement a big unitary on a quantum computer. And as you start increasing the size of the unitary, no classical algorithm will be able to give you a best way of implementing a unitary on a quantum computer. So what you can do, that you apply the bad way of unitary on a quantum computer and then try to learn it using a variation algorithm. I'm being vague here, but there is an application where you have access to training data just because you know how to implement the target function. So this is still sort of an open question in the sense that what are the applications where this result could be useful, where entangled pairs could be useful, and how we can get access to those entangled pairs training set. Another thing which we have not considered, and again, it's a very important question. We try to think about it, but we could not come up with a solution, which is, what if we have imperfect training? So when I was walking you through the proof, I was just saying that, yes, you can just do these averaging over hard averaging of unitaries. But as soon as you have imperfect training, you will not be able to use those properties, that the leftover matrix Y is hard random. So those assumptions will just go away, and then you cannot do the averaging. So we could not figure out a way how to deal with the imperfect training case, and how do we do the averaging? How do we find this average error over all unitaries? And the next part is, even though we could show with the simple single qubit example on the realistic quantum device, Rigetti's quantum device, that you have this feature up to some error bars, you are matching the theoretical bound. But as soon as you start, let's say, adding more qubits and more gates, then we don't know if the noisy training can saturate the bound or even be close to the bound up to some error bars. So these are the 3 questions which we tried thinking about. And yeah, so I think after that, I'm open for discussion. Thank you.
Thanks for a very nice and interesting talk. Does anyone have questions for Kunal? You could use the raise hand feature. I have a few questions that I'll ask in the meantime while people formulate a question. So can you go back to slide 8? And thanks for numbering. Yeah, so I look at the first inequality and I see as compared to the second inequality, there's an additional term plus T over D, right?
Yes.
And then I compare them, and then the permutation matrix is a special kind of matrix. And so the bound, I understand the NFL theorem is like a fundamental limitation on what's possible with learning, right?
Yes.
Yeah. And so the bound on the bottom right is less tight. And so I just wanted to understand that better.
So bound for the permutation matrix will be closer to 0, then this bound. Is that what you mean by less tight?
So if it's a limitation, it seems like if it's like a fundamental limit for any learning mechanism, it seems like it's a better bound if it's tighter, right? And so I'm just trying to wrap my head around that.
Oh, so I think, yeah, maybe I want to be on the same page about the tightness. So when you say tight means smaller, because our goal is to make it smaller.
I meant larger, actually. Like it seems like a kind of, in information theory, we prove converses, right? And so this
So
is
I think
saying,
in this, yeah.
the first one is saying that the error probability is larger, right?
Yes.
Yeah. And so,
So what we are trying to say in this case is, if you know something about the function, then your bound should become smaller.
okay. So like, it means that there's maybe a way to achieve this also.
Yeah, you can achieve this as well. Yeah, this is achievable.
Okay, good.
Yes.
The next question I have, so if you go to the quantum parts, I guess it's a few slides. Yeah, this kind of stuff.
Yeah.
Yeah, you can stick with that slide. I don't know if you remember, I think you were there when Iman Marvian visited LSU. Do you remember that?
Yeah.
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 So he had an algorithm for learning a unitary, and it seems very relevant in this context. Is that something that you cited and somehow
Oh no, I think I missed it completely. Yeah.
Okay. But it seems like it gives you an achievable strategy on a fault-tolerant quantum computer, right? It was like a very interesting quantum algorithm to learn a unitary from a few quantum data points,
Mm-hmm.
right?
Oh, this universal quantum emulator,
That's
that
the,
paper?
yeah,
Oh,
exactly.
I see. Yeah, I should look at it. I completely missed it.
Okay, so it might be good to look at that. I think he still hasn't published it. I think it's just like sit in the archive. It was very interesting. There was a paper.
Yeah, now that you mentioned to me, I remember him giving the talk in one of our rooms on our floor. Yeah.
It was in 435 on the left side.
Yeah. Yeah.
Okay. I have another question. I don't know if people have questions in the meantime, but I'll just go ahead and ask you a question.
I actually cannot see anything, so I'm just staring at my slides. So yeah, I'm okay to.
Oh, that's fine. Yeah, I really like this a lot. So
Thanks.
the metric, if you go to a few, yeah, this one. So you said this corresponded to average case fidelity. And I guess for the classical NFL theorem, that's also very much like there is the metric
Yes.
you start out with, like the average, I guess, Bayes risk, and
Yes.
that average measure also, right?
Yes. So
And then you do further averaging. And so I guess to be fully analogous to that, you do like a quantum averaging here also.
yes, exactly. Yeah. So actually, that's something we spend quite a lot of time on, like putting them on the same footing, which was yeah. So I can actually go one step further, and I can say that this is equivalent to average trace distance square, where
Okay.
average, yeah. So, and then you can also, so when I was explaining the classical NFL bounds in terms of this probability of error, you can translate that in terms of one known distance between two vectors.
Okay.
Unknown, and then that's the equivalence. Like we use the same metric for classical and the same metric for quantum.
Right. So my question was, to me, more interesting, or like the kind of the ultimate error metric would be
Diamond distance.
time and distance. But if you're sticking with fidelity, it would be like fidelity of the channel induced by the unitary. So we could call it like worst case fidelity.
Mm-hmm.
There's a known, I believe there's a known relation, like exact relation between average case fidelity and at least entanglement fidelity when you send in the maximally entangled state. So
Yeah.
can you make statements about worst case fidelity also, or is that somehow out of the scope?
So this is something also I tried thinking about, but the main issue was how do I do the averaging? So this function was nice where I could use the properties of these Weingarten calculus for the Haar averaging over unitaries.
Right.
But for that function, I'm not sure if I can do the averaging easily.
I guess it would
So,
depend. Like if the unitary you're trying to learn has symmetries, then you don't make that.
yeah.
Okay. Maybe as a question, I'll ask a brief question before that. So I think if you advance to your quantum NFL bound, that one, yeah, at the bottom, at the top, yeah. So I was just like, well, that's fine, yeah. So I was just plugging in, and hopefully I'm not committing an error. I can take in your bound R equals D, right?
Yeah.
And then I can take T equals 1.
Yes.
And then we get a negative number.
Yeah. So that's true. But then the which is also like greater than or equals to 0. So
I see. So it's just like for some reason the converse bound is not relevant. But then as you showed, you can actually achieve 0.
yes. Yes.
I was trying to understand what does that mean? Like you learn the unitary in a single shot?
No. So you will have to do the training. So the argument is the following. So if you have R equals to D, you will still do the training process, as I was explaining, that you have the access to, let's say, these training pair. One pair is enough, but you have to do this optimization. So let me just go back to the second slide and then just clarify this point.
Yeah.
So when I went to the third point, when I started talking about scalability, I assumed that my ansatz was expressible enough and my training was also wonderful in the sense that my gradient descent was optimizing to the perfect answer. So the NFL theorem is a statement after you have assumed the first two things.
Okay.
So even if I'm saying that, oh, for the R equals to D case, I can go to 0 average error. Sure, you can go if your answers was expressible enough and your training method was such that, like gradient descent, let's say, could reach to the global optima. And that's why that is also one of the open questions when I think maybe I did not say it, or yeah, I think I did not say it, but that is also another. So imperfect training falls under that umbrella, where if your training method was or your landscape was such that you could not reach to global minima even on the training set, then you cannot reach it. So all these statements are assuming that you learn perfectly on the training data, and then the statement follows.
Okay. Thanks. So, Avi, go ahead and ask your question.
Yeah, my question is with regards to per se a use for all of this would be, say, boson sampling. Has that been considered?
Can you explain, because I have to think about it.
Was boson sampling, the idea was to find the unitary that would do a certain that would be output after you supplied certain inputs to an optical unitary, and you could.
So I think, in a reduced model of quantum computation, like I think, Kunal, in your work, you're assuming fully fault-tolerant quantum computers are available, right?
Yes.
So then,
Yes.
like, if we start considering reduced computational models, do we have intermediate quantum computing NFL theorem?
No, not yet. Yeah. So this is something, yeah, we wanted to try, but we don't have it.
Sounds
so,
like nice
so yeah, that's an open question. Yeah. So, yeah, for the noisy device, how do we phrase all this? Yeah, that's not clear. So we actually suggested this to one of the students, our students, to extend it, but I don't think we have made enough progress.
Okay. Good. Does anyone else have questions? I guess it's been a long day.
Yeah.
So maybe I'll just close out. Thanks to everyone